Swayam Prabha. Digital India. Educated India.
Okay, so in the last class, we discussed about the one-dimensional random walk to describe the key characteristics of Brownian motion, and at the end of it, we compare the results with Einstein's relation or Einstein's solution, and we match the mean and mean square displacement of the two treatments. And as I said before, the Brownian motion was also addressed by Paul Langevin in 1908, and this approach is far more simpler because he starts with a Newtonian kind of mechanics and then adds the extra random force acting on the particle, and then from there he deducts the mean square displacement and other properties. Okay, so this is also very intuitive, very simple mathematical manipulation gives you the results, just like how the one-dimensional random walk problem was. So that will be the topic of discussion today. So the system that we want to study is a particle in a liquid. And we already discussed from the Robert Brown's summary that this particle can be of organic origin or inorganic origin, and only matters was the size of this object. Okay, and it could be dispersed in a simple liquid like water or any other aqueous media, and we know that this particle will execute a irregular dynamical motion. So now when we try to set up this problem in the Langevin approach, so what we do is first we look at what is the law that we know about the motion of this. So we start with this kind of simple Newtonian mechanics, and all we need to do is try to interpret what are the different kinds of forces that are going to act. Okay, so for larger object we know that gravitational force, electrostatic, magnetic, these are all the common forces that we often use, but when you have particles of this kind, we have to take into account of other kinds of forces. Okay, so by looking at what are the nature of this force, we can look at this. So what we do first is this side we write as okay, so we imagine that we look at one-dimensional motion. Okay, and so acceleration is d square x by dt square, and the mass is of the particle, and then what we want to do is, on the other hand, we see what are the forces acting on this particle. Okay, so clearly when this particle moves, it is actually moves in a viscous medium, and as chemical engineers we know that when an object moves through a viscous fluid, there will be a drag force acting on this to resist the motion. Okay, and we also know that the drag force is something proportional to the velocity with which it is moving, with a proportionality constant called a friction coefficient. Okay, and especially if I know the fluid property and the geometry, we can even express what that force is. So we say that this is minus gamma v, this is the drag force acting on a particle moving at a velocity of v. Okay, and this v we can replace as dx by dt. So this would be a classical picture. You know, you have a particle, you know, if you have some initial velocity, initial position, and subjected to this force, you can predict what would be the dynamical motion, and that would be a deterministic model. Okay, but now that we know this particle is also subjected to some other nature of forces, which makes the dynamics very irregular. So on top of drag force, something else is acting on it, and we call that as a random force L. So this is our equation 1. So this Langevin approach is so simple, as I said before, is mainly because it starts with the Newtonian kind of mechanics. Only we say that there is an additional force acting on the particle, and this force will have some sort of a stochastic nature. Okay, so this is not a deterministic force, it is a statistical force, whereas this one is more well behaved deterministic force. Okay, there is no uncertainty about it. You tell me the drag coefficient and tell me the velocity, we know what the drag force acting on it. But this on the other hand has some sort of irregularity. So the irregular motion of the Brownian particle is actually mapped onto an irregular force acting on it. And where is this coming from? It is coming from the collision of this very large number of collisions of the solvent molecules onto the particle at any given moment. Okay. So now we say that this minus gamma dx by dt, this is a drag force, and what this does is it resists the motion. Okay, it tries to damp the motion, that's why there is a negative sign here. Okay, this force acts on the opposite direction of the velocity. Okay, so and then we say this is L of t here. We say that this is a random force due to solvent molecules colliding with the particle. And we say that this has a deterministic characteristic and this has a random characteristics or probabilistic characteristics. Now I am going to take this equation and going to do some algebraic manipulation. Okay. So first what I will do is I will multiply this equation with x. So multiplying equation 1, so on the left hand side we have xm d square x by d t square is equal to minus gamma x dx by dt plus x into L of t. Now what I am hoping to do is, here I have the second derivative with respect to x, okay, but instead what I want to do is I want to convert this equation which will have a term something like dx square by dt, something like this. Okay, why I want this form is because it is a rate of change of the the square, and then I take the mean and I know what results I am looking for. Okay, so right now it is second order derivative with respect to x, and I want to somehow write this in terms of first order derivative with respect to x square. Okay, so that's what I am going to do now. So in this step, I am looking at this particular term d square x square by dt square. This can be written as d by dt times dx square by dt, right. This is second order derivative with respect to x square. I am writing as two parts here. Okay, is it clear? Then I am just expanding this inside, so I am going to get 2x dx by dt, and then if I do differentiate these two terms, I will get, so I keep 2x first and then differentiate this term, so I get d square x by dt square, plus then I keep this term and I differentiate this, I will get 2 times dx by dt whole square. Why I am doing this? Because when I look at this particular expression and it has this term, and this term is what actually factoring in my Langevin equation. So I can replace this term, the x times d square x by dt square, in terms of this minus this. Okay, so that's the reason why I am doing this. So from here we say that x times d square x by dt square is 1 by 2. This term is there, minus this term comes to the other side, the 2 gets cancelled, you will get dx by dt whole square. So now we are going to use this, the expansion of this term via this and substitute it here. Okay, so I have m here and I am just pulling out a factor of 2, so I get m by 2, and I have this d square x square by dt square minus, since I am taking 2 out, I have a factor of 2 here, so I have 2 times dx by dt whole square. On the right hand side I have this term x into dx by dt, that can be written as 1 by 2 dx square by dt. Okay, and the last term remains as such. So if you compare this equation and this equation, so this equation comes from modified Newton's law. What all that we have done here is we are writing things in terms of the differential of the x square. Now we take the average of this expression. When I say averaging, what I mean is this equation tells me about the dynamics of one Brownian particle, but I have very large number of Brownian particles, they are all independently executing random motion. When I say take an average or mean, what I try to do is that average is dynamical equation over all the n particle. Okay, so then what I have here is m by 2 d square by dt square x square. So I am using this symbol for to denote the average. Okay, or I can also put a over bar. Okay, I think either you can use this or use this. Okay, these two mean the same. I mean, if you want to be a little bit more careful, so we use this terminology for time average, and this we use what is called ensemble average. Okay, in the last class I mentioned about doing a time average of force, current, squared and all that. So when we do time average, we try to use this kind of a over bar symbol, whereas when we try to average over a population of objects, then we try to use this angular symbol. Okay, right now it is not very critical whether you are going to use this or this. Okay, so it is some sort of average, time average or ensemble average, they are actually equivalent. So this dx by dt is the velocity. Okay, and we are going to basically write the mean of the velocity squared. Dx by dt is velocity squared and then averaged over. Okay, so then you are going to get velocity average. Okay, or you can also think of this as like this. Or so I am also multiplying by m by 2. So yeah. this term here, when I average over all the particles at any instant of time, the average force vanishes. That is the characteristic of the force that we are saying. Okay, the average random force acting on the system is 0. So when you try to do an average of all the particles, x times L of t will vanish. X is an independent variable, this is an independent variable. Okay, so when you try to write the mean of this product, you will see that the mean of x multiplied mean of L of t, and mean of L of t is 0. Mean of L of t 0 due to the randomness of the nature. So you can see what we have done is we have taken this equation, dynamical equation, and we are writing that in terms of some mean square characteristic. The rate of change of this mean square displacement depends on the mean square velocity and the mean square displacement itself. Yeah. So L is a vector, but here I am talking about a one dimensional problem. I have only x here, but actually if you could write in terms of generalized coordinates like 2 dimension or 3 dimension, then L will be a vector which will have its own components of Lx, Ly and Lz. So now this particular term is called this mv square. It is related to the kinetic energy, mean kinetic energy of the particles, and we know that from kinetic theory of gases, we know that it is dependent on the temperature. Okay, so we apply what is called this equipartition theorem. And that says that half m v square is half kBt. So this is a generalized result. It is applicable for molecules, particles. It applies to you, to me. Okay, it is a generalized approach. But what you will see is that when the object becomes very small, then this mean square velocity is significant. This is what we call as a thermal velocity. Okay, and depends on the temperature. So now what I can do is I can replace this term here with a half kBt. This is a second order differential equation. We will try to write in terms of a first order differential equation by writing the first derivative of mean square is some variable z. Okay, this is like converting a second order ODE into a first order ODE by mapping this. So by this, the first term becomes d by dt of z. This becomes kBt, and on the right hand side we have gamma by 2 z. So this is a linear first order ODE. So the first order differential equation with respect to the mean square is basically written here. I have also introduced terminology gamma by m as the capital gamma. This is because when I have this gamma by m, this will become in the units of time inverse. Okay, it kind of gives a characteristic time. So this will be 1 over time, and gamma here is the drag coefficient like we mentioned before. So then basically you can cast this equation into a linear first order differential equation, and then you can integrate this equation. So I am skipping the steps, it is there in my notes for you to check, but it is easy to see that this function z is given by some constant term plus some another constant term e power minus gamma t. So here the rate of change of mean square, z is nothing but, what is z? Z is d by dt of this. Okay. So the rate of change of the mean square displacement is having a constant term, and there is a time varying quantity. Now if I look at a time scale t, I am looking at an observation at a time scale t much larger than gamma inverse. As I said, gamma has a inverse time scale. So gamma inverse will give you a time scale. Okay. For time larger than gamma inverse, this exponential term will vanish. Okay. What it means is the mean square displacement is evolving and reaching a plateau value. Okay. And that is what this equation basically means to you. So if you look at, make an observation at a t larger than this gamma inverse, you will see z reaches an asymptotic value of 2 gamma by kbt. And this 2, the kbt by gamma is nothing but the diffusion coefficient, and this is known as Stokes-Einstein relation. This definition comes from the Einstein's treatment of the Brownian motion. In the last class I mentioned about the Gaussian distribution for the Brownian particle position. In that the variance was given as 2 dt. There the d was defined as kbt by gamma. This is Boltzmann constant, this is temperature, this is the friction coefficient. Okay, and that determines the diffusivity. When I substitute that here, I show that the rate of change of mean square displacement is equal to 2d, given that you are not looking at a very small time scale, you are looking at a sufficiently long time scale. If you wonder about what is this time scale is all about, we call this as an inertial time. When a particle gets a kick, okay, it has a particular time to relax to this implied force, okay, and that time scale is called the inertial time scale, or the time scale with which the velocity autocorrelation vanishes. Okay, these details we will see when we look at Langevin equation in a little bit more detail, but for now you can think of this time scale is a time scale where the mean square displacement become a plateau value or a constant value. Okay. So then if you know that the mean square displacement is constant, then we can go back to the original definition of z, which is nothing but d by dt of x square, that is a constant. When you integrate this, you will see that the mean square displacement at any time t minus the initial value is 2 dt. Okay, and if I have taken all the particles at the origin to start with, this term vanishes. So I can show the mean square displacement as a function of time t is equal to 2 dt. This result we already predicted from the single one dimensional random walk before, and also we have shown that from the Einstein's derivation of Brownian motion. Okay, so all this theory basically confirms the same result, but the approaches, as you can see, is very different. And you also see that the key ingredient of all these approaches is how they handle the random force acting on it and the statistical properties of that random force. They all say that this is an irregular force, random force, with a mean being 0. Okay, that ingredient is embedded in all these approaches. Here, so I think I would have changed the I would have got gamma here, and then I would have changed back to this. Okay, so otherwise unit wise it should be a problem. I think kbt, this is d meter square per second. Yeah, correct. Yeah. So what I am saying is, I mean, you can still deal with the gamma by m here and then do it, but I think once you group this term, then you can nicely show it as a time scale unit. Okay, otherwise this will become simply a gamma by m. Now let us look at what this time scale means. We will probably try to calculate this for a particular Brownian particle. Let us say I have a radius of the particle is 1 micrometer. So that means the diameter is 2 micrometer, and this is suspended in water. So the solvent is water, or the liquid is water, and we would like to calculate this time constant gamma, which is small gamma by m. Or we can actually even say I'm interested in gamma inverse, that is a time scale. So it will be simply m by gamma, and this would be in the units of time. So this mass is nothing but rho times volume of the particle divided by the drag coefficient, which is 6 pi mu r. Okay, so this comes from Stokes relation. So pi cancels. So you have 2 by 9 rho r square mu. So we take, by the way, rho is the density of the particle. We will assume this to be 1000 kg per meter cube, same as that of the solvent. And the viscosity of water is taken to be 9 into 10 power minus 3 Pascal second. Sorry, the viscosity is taken to be 10 power minus 9 minus 3. So this comes out to be about 0.2 microsecond. So this is the time scale I was talking about here. So at a time scale t larger than this 0.2 microsecond, then this mean square displacement will become constant. So what happens if you make an observation shorter than this time scale? Then you will see that the mean square displacement that you see here will not be as simple as this, but you'll have a time characteristics also. Okay. In another approach, which I will be doing in the next class, we will also try. So what is missing in this entire approach is what is the nature of the velocity of the particle that is moving. Okay, so we look at how the velocity is developed and how that it decays and how that translates into mean square displacement and all that. Okay, so that would be the content of the next lecture, but for now I think we'll stop here. Any questions on this discussion today? Yeah. Yeah, we have assuming temperature is constant. Yeah. Just go through your notes and then ask me if you have any questions. Suppose if I ask you to calculate a time required for a particle to move its own size, how would you calculate? You understand the question? The particle is diffusing out, right? And you want to know how much time it will take for a particle to move by its own length and an average. What would that be? How do you calculate this time scale? In other words, I am asking diffusion time scale. You have something? Mean free path. It is applicable for kinetic theory, but here we are talking about this diffusion as the dominant mechanism, right? So, in the mean free path approach, you are talking about gas molecules colliding with each other, and between those collisions they travel in straight line and more deterministic way, right? So, here we are not talking about that. We are talking about a larger particle undergoing a diffusion because of the nature of the surrounding, and we are asking what is the time scale. Can you give me an expression, or how would you, I mean, is it something that you are going to numerically solve and get it, or is there a, yeah, yeah, yeah. Mm-hmm. But there is a much more simpler way to do it, right? I mean, so you can define something like r square divided by d. So this actually gives a time scale for diffusion. Okay, so how do I get this? I get this from the fact that I know that, okay, so this is a mean square displacement behavior of a random motion particle. So here I am interested in for a given given distance that it has to travel, what is the time required. So from here you can show the factor of 2 is not there, but you can see the relationship, these are actually essentially the same thing. Okay, I am replacing the mean square displacement for the size that it wants to travel, and the time I am interested in is this tau. So this gives what is called this diffusion time. As an exercise, you go back to this problem. Here we have found what is the momentum relaxation time, or what is the initial time, which is about 0.2 microsecond, after which the particle reaches a constant rate of mean square displacement. Now you calculate the diffusion time for this particle by that expression and compare what is the order of magnitude difference between the time it takes for a particle to move and an average to its a mean square displacement equal to the size versus the momentum relaxation time. So what you need to calculate that is, you need d, and d is obtained from kbt by 6 pi mu r. You need a temperature, take 300 Kelvin or so, and you substitute that and get a d, and then use that expression to get the diffusion time scale, and compare that diffusion time scale with this. Okay, so if you do that, you should get something about tens of seconds, or so we are talking about some 6-7 orders of magnitude difference between the time it takes for its move versus the momentum relaxation time. Okay.